Hello, everybody. So in this particular video, we're going to discuss eigenvalues and eigenvectors, two of probably the most important computations we do in all linear algebra, and they have enormous impact throughout mathematics and in many other subjects. So to lead you into it, let's go back over a problem I did before. I mentioned what was called a Markov chain. So then let's go review the idea. We had two brands of toothpaste that were competing with each other. Brand A, after 1 month, would continue to retain about 70% of its consumers, while it would lose 30% of its consumers to brand B, while brand B, 80% of that brand would then stay with brand B, but 20% would then switch to brand A. We wanted to know in the long term what percentage would favor one over the other. So then we found out that there was a nice matrix multiplication that we could multiply out in order to determine the percentage of people, which we write here as A sub n, that would prefer brand A after n months, and the percentage of people that would prefer brand B, which here is B sub n, after n months. And it was this nice matrix power multiplied to a vector where that vector was supposed to represent the percentage of people that in the beginning preferred brand A and brand B. So in the beginning, we're assuming here that 50% of people prefer brand A and 50% of people prefer brand B. So to get an idea of how we're going to eventually lead to eigenvalues and eigenvectors, let's suppose for a second that the vector x is considered a probability vector. Now, a probability vector means that all the components in that vector add up to 1, and they're all non-negative. They can be 0, but they have to be at least positive or 0. Well, if that's true, though, notice that if you take the matrix A times X, just doing the matrix product, you would get this weird vector whose components involve A and B and a bunch of numbers. But take that new vector and notice it's actually a probability vector, because if you take those entries and just add them together, it's actually the same as A plus B, which we assumed at the beginning was 1. And clearly, if A and B are positive, then that product is also both of those entries being a sum of products of positive numbers would also be positive. So the result would be a probability vector. So that's nice to know. But also, what we'd like to know, though, what happens if we just take this matrix to a ridiculously high power and then multiply it on the right by the vector 0.5, 0.5. Does it tend towards anything as n gets large? And I showed you last time, a couple videos ago, that it seems to tend towards some vector whose entries add to 1, but who it looks like it's like 0.6 as the first entry and 0.4 is the first entry and 0.6 is the second entry. I want to give you a reason why that should be true. To do so, though, we have to think in more calculus terms. I want to take the limit of this expression that you see right here, and I'll find out what happens to that product as n becomes 1, 2, 3, 4, and so on, becomes incredibly large. To do that in calculus terms, we express the idea in limits. So let's suppose that A is the matrix, P is the initial probability vector, where we're assuming both of those is 50%. And then the product of A to the nth power times this probability vector in the limit would become a vector X. I want to know what would have to be true about this vector X. Well, what happens if we took A times X then? Well, X is this weird limit thing. One of the properties of calculus, though, is that you can swap orders of constant multiplication and limits, and a matrix is kind of like a constant multiplication. So you can swap those, but then you have A times a product, where that product is a product of other matrices. You can then reassociate and write the product instead as A to the n plus 1 power times P. But once you do that, this thing here is really the same as that there. The only difference is the power is just 1 greater. So we get to whatever we're approaching just that much faster. So the limit then has to be what this limit approaches, which is X. The important thing, though, is whatever this X is, it must satisfy that interesting equation. So let's go sit down and try to figure out how we can solve that thing. So In order to do so, I'm just going to do some clever rewriting of expressions. The x you see on the right-hand side of that equation, you can think of it as the identity matrix times x. But then I could bring all the matrix products to one side and collect variables by using our properties of matrix multiplication to get that equation. What's important here is that the matrix A minus I, that matrix, which is a 2 by 2 matrix, times this vector x equals 0. That means then A minus I has a non-trivial null space. Remember, because null space is just the set of all equations, the set of all solutions of that equation, where the matrix times something equals 0. And we know at the beginning that this vector is non-zero, because if it was 0, it would make no sense, right? All the entries are all bigger than 0. It has to be bigger. It has to be non-zero in the end. Well, let's just do the computation. Let's try to solve that system. So I'll say the vector x has entries of a and b, so I don't have to call it x1 and x2. I just take those matrix, the matrix A minus the identity, and I simplify it. I then take that system as an augmented matrix and I row reduce it. And once you row reduce it, I can then see there will be a free variable because the two rows would then be multiples of each other. So therefore there'd be one free variable. And once you go through the process of solving, you'd see that A equals 2 times t and B would be 3 times t. So t could be anything you like, and you would get another solution to the system. But we're interested in the solution where these entries, A and B, add up to 1. So if A and B are going to add up to 1, that would imply then A plus B would equal 2t plus 3t. That's 5t, but that has to add up to 1. So t here must be a fifth. So then I'll use t as a fifth to find out what A and B must equal. So then if x is anything, if this works at all, then the entries of this vector have got to be 0.4 and 0.6. So that's what we suspect. We suspect then if we take the matrix to a large power and then multiply it on the right by the vector 0.5, and 0.5, that we approach the vector 0.4 and 0.6. Let's just test and see what it looks like. So then here, I'm just going to take the matrix product you see, and I'll evaluate it when n is 1, when n is 2, when n is 3, when n is 5, when n is 10. And notice you can see that the vectors certainly appear to be approaching the vector 0.4 and 0.6. But actually what's really, really interesting is if you go back and look at the way I argued, the vector p didn't matter. The only thing that mattered is it was a probability vector. Me starting with the assumption that we start off with 50% of the population preferring brand A and brand B was arbitrary. So I suspect then that it doesn't matter what P is as long as the entries add up to 1. We should get a probability vector at the end, and it should approach the vector 0.4 and 0.6. So here I did the same thing. I just picked a different initial probability vector. Here, I'm assuming that now only 20% prefer brand A and 80% prefer brand B. And looking at the process, you can see, yeah, it appears that it approaches 0.4 and 0.6. So obviously that equation, AX equals X, is kind of important as it leads to a really neat application. It gives us a feeling for how a population, or at least market trends, would turn in the future and what they will tend towards in the end. I think that's enough for now, for that video at least.